giving me the opportunity to talk here. So the the aim of the talk is to give an update on what's the status of the classification of tight context structures on Seifert fibered spaces. And so, the long-term aim is that suppose Y is a closed-oriented three-manifold, and try to classify context structures on Y, well, sometimes up to contactomorphism or isotopy. So this is sort of the motivating problem. And of course, as we already heard this week, there are, context structures are not created to be equal. There are tight and over-twisted ones, and the over-twisted are already classified by their homotopy theory. So we just take the assumption that we are only concerned about tight structures. And there are a few simplifying assumptions we can make on Y. The first is that so tight structures admit unique prime decomposition, by which I mean that if you have a three-manifold which is a connected sum of two others, and you have a tight structure, then it can be presented as a contact-connected sum of two uniquely determined tight structures. So we can sort of restrict ourselves to prime manifolds. And also, there is a sort of coarse classification which is due to Colin, Vincent Colin, Emmanuel Giroux, and Ko-Honda, which sort of puts three manifolds into two classes, depending on whether they contain an essential torus or not. So it just says that if the three manifold is toroidal, then there are infinitely many tight structures, and for atoroidal, there are finitely many. There are at most finitely many up to isotopy. So somehow the lesson is that tori, essential tori, are useful in answering questions regarding existence. You can construct tight context structures. In fact, you can construct infinitely many. But when it comes to the complete understanding, then they are somehow troublemakers. And you don't know whether these constructions will interfere and produce the same structures by different methods. So I would like to focus on this bracket today. And of course, these manifolds come in two flavors. They can be hyperbolic and Seifert fibered, and I will concentrate on Seifert fibered. And we almost have a complete picture for the Seifert fibered case. So if you would like to sell the theorem, you would say like half of the case is done. Of course, if you buy it, you would say like 0% of the manifolds are done. But let's sort of put it under the rug and let's not talk about that. OK, so up to contactomorphism. Yes. 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 So there is this sort of significant piece inside the contact manifold, which is invented by Emmanuel Giroux, this Giroux torsion, and this will distinguish them. OK. So a few sort of important steps in this kind of questions. So the simplest case, S3, here the classification is due to Eliashberg. And of course, the important step is to understand what happens if you have a context structure on a disk, where the context structure is somehow given already near the boundary. And Eliashberg's result is that if you pick the appropriate boundary, if you pick the appropriate context structure near the boundary, then there is a unique tight extension. So this is a uniqueness. And a somewhat similar idea, now instead of understanding tight context structures on the disk, but trying to understand tight context structures on the solid torus, provides classification for length spaces. So this was done by Emmanuel Giroux and co. And so let me just spend a few minutes or a few seconds in explaining, at least giving you the statement. So for me, length spaces are defined by a very simple surgery diagram. You take the unknot, and we take minus p over q surgery. And obviously, this uniquely determines a three-manifold. But if you work a little harder, not much harder, then you can actually associate a four-manifold to it, which is somehow a surgery along a chain. Where these integers are determined by the continued fraction expansion of minus p over q, and all the ai's are less than minus 2. And so how to turn such a diagram into a context structure? Well, as we learned in Ty's lecture, I'm not planning to talk about joint projects or theorems, but at least I will refer to the lecture. So you turn this knot into a Legendrian knot. You turn this link into a Legendrian link by just taking the Legendrianization of these guys, and so on. And then you would like to perform surgery such that smoothly it gives back what was originally there. And you have to take into account the sort of reference framing. For a smooth picture, you always use the Seifert framing given by a Seifert surface. When you have a Legendrian knot, then there is another convenient framing, namely given by the context structure. So this is called the context framing. So the difference between the two in the case of the unknot is just minus 1. So here you need A1 plus 1 surgery, A2 plus 1, and so on. Remember, these are all negative numbers. So in absolute value, you sort of make it smaller. And to make things more convenient, we would like to sort of come up with links where we only do plus or minus 1 surgeries. And the reason is that when you study, so how do we do surgery? We just take a small tubular neighborhood of this knot out, and there is some leftover context structure near the boundary of this torus, and we just glue it back in some way. And the question is, how many different ways can we extend the context structure such that it will be at least tight on the extended torus? So let me just give you a sort of a pictorial explanation of what I was saying. So we take out a knot. What we are left with is a three-manifold with boundary. And we would like to glue back S1 cross D2 with some diffeomorphism. And we have a context structure right here, which gives you a context structure near the boundary. And the question is whether we can, and if we can, how many different ways can we extend it to this to the solid torus such that it is at least tight in the torus. For this, one has to understand tight structures on the solid torus, and this has been done. And the extension will be unique, provided you do surgery with coefficient plus 1 or minus 1. So we will be very much in favor of these two specific framings. So here, of course, we have other negative numbers. And to match with the plus 1, minus 1 requirement, we'll just change the difference between the Seifert and the context framing by introducing stabilizations, as Ty explained. So if I introduce a stabilization right here, then my coefficient will change to A1 plus 2, and I do it until all the coefficients become minus 1. Of course, there are many ways to do that, because it turns out that stabilizing on the left or stabilizing on the right gives you different answers, but what really matters is how many times you stabilize on each side. So that gives you sort of a combinatorial count, in how many different ways you can turn it into a diagram which smoothly still looks like that. All these numbers become minus 1, and you do the right surgeries. And so the result is that these are all. So this procedure gives a number of context structures, and the theorem is that these are all. Of course, in order to show that these are all, you have to apply some contact topological arguments, and also you would like to be able to distinguish them, and here is the way to distinguish them. So this construction on the three-manifold level gives you a three-manifold equipped with a context structure. But it also gives you something else, because there is a four-manifold behind this whole construction, and the construction also gives a four-manifold, and again, referring to Ty's lecture, it comes with an extra structure. It comes with what's called a Stein structure, together with a Stein structure. And as such, it provides, let's call this four-manifold X. So it provides us a first Chern class of the Stein structure, which lives in the second homology. And indeed, by a result of Paulo Liska and Gordana Matic, if you have two pictures of the same four-manifold with different zigzag distributions, giving you different first Chern classes, then the context structures will be different. You don't need this here, but there is like a pedagogical reason we are doing that. Okay, okay, give me a little time. So these Chern classes distinguish the context structures. Indeed, in this case, the spin C structures induced by the context structures would also distinguish them. So as Patrick pointed out, there is a sort of a, how shall I say, lower tech answer for that. But as we will see sometimes, when we work with Seifert fiber spaces, then things will be a little bit different. Okay, so this is what we have about length spaces, and in fact, one can come up with the actual exact number, how many different tight context structures we have. So consider now Seifert fibered spaces. And we would like to stick to this atoroidal case, so I will only concentrate on Seifert fibered spaces over S2 with at most 3 singular fibers. Over S2 with at most 3 singular fibers. In fact, I will always assume that we have exactly 3 singular fibers, because length spaces are already considered. So let's define the Seifert fibered space E0, R1, R2, R3 by the surgery diagram of having 4 unknots linked in this obvious way, and we do surgery -1 over R, -1 over R1, -1 over R2, and -1 over R3. So this is my definition of this Seifert fibered space, where I assume that R1 is bigger than R2, bigger than R3, and all Ri are rational and between 0 and 1. So this sort of gives a presentation. And we can try to do the same as we did above. So step 1, there is a 4-manifold xy associated to y by doing exactly what we did up there, by substituting the single surgery with a chain of unknowns, and the surgery coefficients are given by the continued fraction coefficients of the framing. And I will not write down the details, but this is what you do. So the framings are A1, A2, A3, B1, B2, and so on, C1, C2, A0, and AI, BI, CI are all at most -2, and A0 is just an integer. So let me just tell you a few simple observations, so simple facts. So the first is that Y is a rational homology sphere if and only if the number we get by adding these parameters up, E0 and all the Ri's, is non-zero. And what else? XY is negative definite if and only if this number is negative, and it has B2 plus equals 1 if this number is positive. We can understand what are the coefficients of minus y, and I will just write that down very quickly. So this is like minus E0 minus 3, 1 minus R1, 1 minus R2, 1 minus R3. OK, so these are the gadgets we would like to work with. And let me sort of state one more simple construction here.
Why is the boundary of x sub y?
Say it again.
Why is the boundary of x sub y?
Yes. And indeed, if we take x sub y and we glue it to x sub minus y, then what we get is a blown up Hirzebruch surface. It's CP2 blown up some number of times. And in fact, you can sort of see how this construction goes. And I will be very vague and sketchy in that moment. We just take a Hirzebruch surface where the 0 section has self-intersection E0, and the infinity section has self-intersection minus E0. And then we take 3 fibers, and then we just try to embed or graph or plumbing graph y into this picture by first blowing up 3 times along these points. So what we get is minus E0 minus 3, E0, and then rational minus 1 curves. And when we just keep blowing up these curves until we see the appearance of the graph associated to that plumbing. And what's left over on the other side, it's not hard to see that it will be exactly a plumbing graph of x minus gamma. So these are sort of the inputs we would like to keep in mind. And so let me sort of collect the results which were already known for this for the classification of tight structures on those manifolds. So the story sort of falls into 3 components. The first is when E0 is less than or equal to minus 2. So in this case, all framings in the diagram of xy satisfies the assumption that they are all less than or equal to minus 2, right? On the leg, on these 3 legs, all the surgery coefficients are less than or equal to minus 2. And in the middle, we just know that it's an integer, but now we assume that it's less than or equal to minus 2. So this strategy, how we built context structures for length spaces, just works perfectly. So the same idea, the same construction as for length spaces works and gives many examples with a property that they are all Stein-fillable, since not only the boundary is constructed in the same way, but the four manifold will have the same kind of property that we just apply contact minus one surgeries. And what else do we want to say? And they are all distinct. And now the theorem so the proof is due to how vu in the case when E0 is actually less than -3, and Paolo Gigini if E0 is -2 and Y is an L space. And that's a recent result of Bülent-Tosun for E0 equals -2. So this is sort of a long line, and the theorem will be very short, which says that these are all. So somehow the picture is very similar to what you saw for length spaces. There is an obvious way to construct contact structures. They are all Stein-fillable, and somehow the Stein filling itself distinguishes them. Yeah, OK. So did I say that? Maybe I didn't say, but this is why I introduced this EY, this invariant. So we always assume that we are dealing with rational homology spheres. So I always assume that that sum is not equal to 0. Sorry. Yeah, maybe I will just put it here. So EY is not equal to 0. Indeed, this is a vacuous assumption if E0 is at most -3, because there is no way you can add up to 0 by 3, you know. We all know that, right? So I can erase that. OK, so the next thing is when E0 is non-negative. Then we need a little bit of a trickery, not much. So how is the surgery diagram looks like this. And so on. And we can almost imitate what we did so far, because most of the framings are less than -2, less than or equal than -2. But there is this middle one, which is a non-negative number. So what we can do is we just blow it up. We just apply this simple operation of changing the four manifold in a simple way, but leaving the three manifold intact until this framing becomes 0. And then we do another four-dimensional operation. When you see a sphere in a four manifold with self-intersection 0, then you can surgery it out. You can replace it by a one handle. So we replace the 0-framed circle by a one handle, which in Agbulut's-Kirby calculus notation requires the addition of a dot. So this just means that we are taking, instead of the 0-framed sphere, we just take a one handle. The boundary will be the same, and then we build the rest on the same boundary. OK, so now we can attach a Stein one handle, and then the rest works exactly like before. So in this case, the same Stein handle attachment works. Well, we don't use the original diagram. We did this little massaging of like dropping it down to 0 and then doing the surgery. In fact, if we would like to phrase it in terms of these similar diagrams, we will need one simple observation. I sort of alluded to the fact that if you have a Legendrian knot, say a Legendrian unknot, then it is safe to do -1 surgery because it uniquely determines a tight structure, or it uniquely determines a contact structure by taking the tight extension. but you can do a +1 surgery as well. So we can do a +1 surgery, which will have the same effect as doing a smooth 0 surgery, except now Eliashberg's theorem just breaks down. Somehow the Stein structure, which you see on the 4-ball, will not extend to a Stein structure. But it's a little price to pay. So in this case, in fact, we can come up with a surgery diagram, a contact surgery diagram. I will just try to draw it. And this is a good practice because I will be drawing this picture many more times. So these are these 5 Legendrian knots, the central one and the 4 on the legs. You do +1 surgery on one of them, and then on the others you do negative contact surgeries. So you just use the strategy we had for the lens space. You just take the continued fraction expansion, and everything works fine. So again, the upshot is that even in this case, everything goes through what we said before. All the contact structures are Stein fillable, and they are distinguished by either the homotopy type of the 2-plane field, or you can just consider the Stein 4 manifold, or the Stein structure on the fixed 4 manifold, and consider its first Chern class. Okay, so this is where we stood a few years ago, and then there is one missing case, the E0 equals minus 1. So the last problem is when E0 is equal to -1. And again, secretly, I am always assuming that we are not considering the 3 manifolds which are not rational homology spheres. And so we should expect some complications here. So there are a few facts which we knew about these manifolds. So the first one is that, unfortunately, there are, or I don't know, fortunately or unfortunately, there are examples carrying no tight structure. Of course, you have to be a little bit careful with that sentence, so by which I mean that they don't carry positive tight contact structures. So if you reverse the orientation of the manifold, then they will do, because they will fall into that category of having the central framing -2, and they all do. So I will just write down which guys have this property. These are the ones with 1/2, n over 2n plus 1, and 1 over 2n plus 3. So where n is a positive integer. So the first of this sequence was found by John Etnayer and Co-Honda, and then with Paulo Lisca we sat down and tried to implement their technique, and they worked for this entire family. So we have to be careful, and it's clear that we have to have some more refined technique to prove anything for these guys. The next thing is that there are tight but not fillable structures. And I give you one example here. So now we take the Legendrian trefoil, and we do +1 surgery. So the obvious reason doesn't tell you that it's a fillable, Stein fillable structure. And indeed, it is tight, which needs some kind of an argument, which I will get back to that. But this is not fillable by topology. So it's somehow not the property of the contact structure, but it's a property of the 3 manifold. And let me just sketch a very quick argument for that. So this 3 manifold, Y, is an L space. And there is an argument using either Seifert-Witten theory or Heegard-Floer theory saying that if it has a filling, it has to be negative definite. On the other hand, this is a well-known manifold, and it admits another concave filling or a concave cobordism where the intersection form is, I think it's minus E7. So this is negative definite, this is negative definite, so Donaldson's theorem kicks in, and it says that the intersection form of this four manifold should be diagonalizable. And well, we know that minus E7 is not diagonalizable, but that would be not enough. This minus E7 is such a tricky intersection form that minus E7 does not embed into any size diagonal form. And that's what we really need. And in fact, it's not hard. It's like a high school type exercise. So somehow the topology of the three manifold prevents whether a structure exists or not. It doesn't matter. There is no filling. OK, and there are other examples. So let me just give you one more example. So if we take these Seifert fibered spaces from the same family, then they admit Stein fillable and not fillable contact structures, tight contact structures. So the argument should be tricky. I mean, it's now the topology does allow the existence of a Stein fillable contact structure, but some other obstruction forbids that certain other tight ones are fillable. So it's clear that we have to have a more refined approach to these manifolds. And there are some partial results regarding classification. So let me try not to make mistakes. So here is a family, y minus 1. I didn't realize that I wrote with such little letters at home. OK, minus 1. So classification is known for this. This is work of Paolo Gigini and Jeremy. And I forgot to mention that these contact structures have a further peculiar property. There are strongly fillable but not Stein fillable examples. And then there are a few further families, and I will not sort of particularly detail which families are already known. Let me just mention one more result, and then we can just move on. So, OK, symplectically fillable. So there is a symplectic filling, but you cannot make it into Stein. But somehow, in that sense, for these manifolds, there is no real distinction by strong and weak, where, because these are rational homology spheres. OK, so one more remark. So as far as construction goes, these non-existing guys are sort of frightening. And so there is a result of Paolo Liska and myself saying that, indeed, all Seifert fibered three manifolds except the ones in the other blackboard up there, here, do admit tight contact structures. So the reason why I sort of listed all these results is to show that, OK, Seifert fibered spaces are very restrictive when you compare it to hyperbolic three manifolds, but they sort of show all kinds of strange or complicated or odd behavior, so we can sort of consider them as a reasonable sandbox to play around. But the situation is not that bad. We do have tight structures on most of them, except a few, like a one parameter family. Unfortunately, we have no clue whatsoever what happens for hyperbolic manifolds. And notice again that although these guys do not admit positive structures, they do admit negative tight context structures. So
All the structures covered in the other case, in the negative orientation?
no. It's you shouldn't expect that. Typically, like a small portion of the species structures, yeah, except some like S3 and some lens spaces sort of cover a lot. But even for lens spaces, there are ones which are not covered, as again referring to Ty's lecture.
No, I for the ones that don't have any tight structures, then you look at the reverse orientation. How many species structures are covered?
So those manifolds actually are addressed by John Etner and Bülent Tosun, and they have some kind of classification for them, but I don't know. I don't know exactly. Okay, so what I would like to do now is to move on, and so we take this case, and having all these difficulties in mind, we'll restrict ourselves to one class of such manifolds and assume that Y is an L space. So this is the class for which we'll have a classification, and for the non-L space case, so some families which are non-L spaces, Bülent and John had some ideas how to actually do the classification. So instead of telling you what the definition of an L space is, because we talked so much about them, let me just remind you that this condition is the same as not having transverse foliation or not having a taut foliation, or actually there is a numerical condition which comes from earlier work, says that this is equivalent to saying that there is no such pair of integers m and a such that m is less than 1 over R3 and a satisfies these inequalities. So this is somehow a condition which can be very conveniently used on the diagram. And so so how shall we prove that whatever construction we apply, the result will be tight? That's a main question. And here is a proposition which I will write down. And so here is the constructive side. So this is still an older result of Paolo Lisca and myself. So suppose that Y is an Y minus 1, R1, R2, R3 is an L space, and Xi is a tight context structure on Y. Then Xi can be given by the following surgery diagram. So I will just copy practically this diagram and give different framings on that. So we have to draw 5 Legendrian unknots linked in this peculiar way. So instead of having 1 plus 1 surgery, now we have to do 2 plus 1 plus 1, and all the others do the surgery which is required by the topology of the 3-manifold. Again, these are not plus or minus ones. These are like negative rational numbers. So what you have to do is to expand them into continued fraction expansion, add further curves or knots. I don't want to draw them, and then add the necessary number of zigzags. So this picture, in fact, determines a finite number of contact structures. Some of them tight, some of them not tight. But the theorem says that all the tights will appear among them. So from now on, the game is we have this family of pictures, and we have to decide two things: whether the picture gives you a tight one or not. And the second is that if you have two pictures, can you distinguish them, or they are isotopic? So this is the main result, which I would like to explain how to prove. So this is a theorem, a recent theorem of a student of mine, Irena Matkovic. I don't know. Either this or that. Which one? Yeah. Yeah, this Turkish thing didn't sell very well. But okay. So here is the statement. So suppose that y is y minus 1 or 1 or 2 or 3 is an L space. Then psi context structure given by such a diagram is tight if and only if, and now I will just give a numerical condition, and I will tell you how to read off these numbers from the picture. So some number associated to the diagram is equal to some other number also associated to the diagram. So I will explain these two letters in a moment. And the second is that psi1 and psi2 are context structures given by such diagrams are isotopic if and only if the spin C structures induced by them coincide. So, what's the implication of this theorem? Well, I have to explain what these numbers are, but suppose these are numbers which can be easily read off from the diagram. So you have to sit down, draw all these finitely many possible diagrams, compute these numbers, and then you can select out the tight ones by this condition. And if these two classes coincide, then the relevant diagrams are isotopic, and otherwise they are not. So it's a classification in the sense that, I cannot predict, or we cannot easily predict how many tight structures you will have on such a manifold, but there is a finite recipe, which is sort of a simple recipe to tell what exactly are the tight structures on the manifolds. Is there any question besides what these numbers are? So these are the induced spin C structures. So a spin C structure on a 3-manifold is an equivalence class of 2 plane fields, and every context structure is a 2-plane field itself. So we can just take its equivalence class, and this is what T psi is. So, one way to sort of interpret this property of tight context structures on these manifolds is that they are like very close to being over-twisted. Somehow, it's not even their homotopy type of 2-plane fields, but only the spin C structure of the homotopy type of the 2-plane field. That classifies them up to isotopy. So they are really on the borderline, which you would sort of expect because there are so many non-fillability, and there are manifolds which do not admit any tight structures, in fact. So they are like one step away from being over-twisted. Okay, so So what are these two numbers? Let me just spend a little time. So the D3 invariant, D3 of psi, is exactly the difference between having a two-plane field and a spin C structure. So there are many homotopy types of two-plane fields induce the same spin C structure, and they are distinguished by a number which is a Hopf invariant, and this admits a very nice description in terms of almost complex structures. So suppose that xj, almost complex, four-manifold, bounds, admits y psi as its boundary, by which I mean that the boundary of x is y, and psi is the two-plane field given by the complex tangencies of xj, then here is the formula for computing that particular number. It's 1/4 C1 square of xj minus 3 signature minus 2 Euler characteristic. And there is somehow a constant problem of how people interpret Euler characteristic. You would think that there is only one good way to do that, and that's true, except sometimes we like to view x as a compact manifold with boundary y, and sometimes we would like to see it as a cobordism from S3 to y, and that gives an ambiguity of 1/2. And just to confuse you, I will do this other thing, that it's a cobordism from S3 to y. Okay. So this is the definition of D3. How can we read it off from a diagram? So for a given diagram, after we expand all the rational numbers to integers and we have a four-manifold in the background, we can take the four-manifold, which I denote by x, and consider C to be C in the second cohomology, which evaluates on the basis element given by a knot as its rotation number. So, we have a surgery diagram. Every knot is responsible for a homologous class in the resulting four-manifold, and this cohomology class evaluates on that homology class exactly given, the number is given by the rotation number of the knot, which is like, loosely speaking, is how many left and how many right zigzags did you add, and you have to just subtract the two from each other. Okay, so, well, this is true. Okay, that's what it is. And now it turns out that this class C is indeed C1 of xj, provided we have only -1 surgeries. And then we just plug into this formula up there, and we get the D3 invariant. If for +1 surgeries, we have to modify the formula a little bit. Namely, we just take the same class, and then we have to add the number of +1 surgeries. So this is what we expect from, this is this D3. So by this algorithm, it's sort of very easy to determine that number. And so what dt psi is, let me just start here. So I don't want to go into any kind of depth of like sketching how Heegard-Floer homology is defined, but let me remind you that this is a machine which, when you are given a rational homology sphere, it associates a finite dimensional vector space, and we always use Z2 coefficients just to be on the safe side, and an FU module which is of rank 1. So this looks like a free summand plus some torsion. And both the vector space and the module are both graded. And the D invariant is just the grading. With a spin C structure. And the D invariant is just the grading of the top generator. And so this, again, in order to identify this number from the picture, we have to be able to identify the spin C structure. But luckily, this is exactly given by that class. Notice that this is a second cohomology class on X, and it's not very hard to see that it's a characteristic class. So it uniquely determines the spin C structure, and peak psi is exactly the restriction of that spin C structure to the boundary. So if we know how to compute Heegard-Floer homology groups for 3 manifolds and spin C structures on them, which is the case for Seifert fibered spaces, then there is a simple formula to determine this number. So how to apply this this theorem, or this how to derive this? Okay, so I will give you a sort of a sketch of the argument. So we have two problems. We have to be able to systematically decide how this equation implies tightness, and also how to find isotopies between seemingly different structures. And so the idea is the following. So let me sort of draw the 4 manifold. This is X gamma. You remember when we took X gamma, XY, and X minus Y, then when we plug them together, we got a blown up CP2. So here there is a plumbing manifold. It's a plumbing manifold. There is a plumbing along a star-shaped graph with 3 legs, and the same appears on the other side. This is my side, starting with a -1, and there are all kinds of further vertices with framing less than or equal to -2, and here we have a -2. The first observation is that altogether we have b plus equals 1, and it should be distributed by this being negative definite. And this has b2 plus equals 1. That's sort of not hard to determine because this is an L space. And now what we would like to do is to sort of getting a hold on that number, but from the other side. So this is a negative definite 3 manifold. This is a negative definite 4 manifold, the plumbing. So there is a way to capture Heegard-Floer homology elements on that manifold by using Peter and Zoltan's picture of Heegard-Floer groups of boundaries of negative definite plumbings. And so let me just give you this this definition very quickly. So let me just first give you the moral. So what happens here? We have this manifold. Actually, this is minus y, and this is S3. And there is a 4 manifold, x minus y. So, and this is negative definite. So what you can do is to consider all kinds of spin C structures on that manifold. So consider a spin C structure on x minus y. And a spin C 4 manifold will induce a map from the spin C boundary, one spin C boundary to the other. So this will give us f x minus y from age f S3 to age f minus y. And so say we stick ourselves to this head theory. This is just Z2. So we hope to apply this function to the generator of that guy, and we will create elements there. Of course, you know, there are several problems. For example, this element can be 0, or different spin C structures will map to the same element. So this is what one has to sort out. And this leads to the following definition. A sequence K0, Kn on a negative definite plumbing X is a full path if it satisfies the following properties. So ki plus 1 is ki plus twice the Poincare dual of a vertex of the plumbing if ki evaluates on the vertex as its negative, the negative of its self-intersection. K0 satisfies which one? And Kn satisfies this inequality. So there are some inequalities which sort of keep some control on what this map is supposed to do. Practically, it sort of controls the adjunction type inequalities. And so the statement of Peter and Zoltan. Oh, sorry. These are homology classes or equivalently spin C structures on the 4 manifold. And you go from one to the other by taking this sequence. And you expect that within one sequence, they should give the same element. And there will be one more condition when this element is 0. So such a sequence provides a non-zero element in age f hat minus y. And if starting with k, we get ki satisfying that this term somehow drops out of that inequality, then the corresponding element is 0. So what do? We have, so I'm sort of a little bit out of time, but so here is the very quick idea of the proof. We consider this 4 manifold, which for the homologies are generated by the hyperplane class and the exceptional divisors. And we consider cohomology classes, which are Poincare duals of such sums where epsilon and epsilon I are both plus or minus 1. So we have lots of such classes. We pick those which restrict to this side as is dictated by the rotation number of one psi. So we start with a psi, and we would like to see whether it is over-twisted or tight. So this sort of selects a few of these vectors. And the statement is that if the restriction to the other side gives us a vector k which fits in a full path, so it gives you a non-zero element, then we know what the degree of that non-zero element is. It should be exactly dt psi, because that's the only non-zero element there, because we are working in an L space. And then knowing that, you just can relate the d3 from this side and the d from that side, and you realize that they are equal, and that will imply the tightness of the structure. And you get a non-vanishing of the contact invariant. And then what is really sort of nice is that if you have two structures, psi1 and psi2, and you pick two such vectors, then you would, if they generate the same non-trivial element in Rey-Floer homology, so they are both tight, then this sort of sequence of steps tells you how to hope for finding an isotopy between them. And then the real work is actually to prove that these steps, these inductive steps, induce an isotopy. And that's sort of the idea. Of course, the details are a little bit messier than that, but I think this is a good moment to stop. But before doing that, there are two things I would like to tell you. The one is, that's the one, that next June, there will be a conference which sort of celebrates the 70th birthday of Ron Stern and Ron Fintuschel, and also brings together mathematicians and the usual topological stuff. So this is called Perspectives in 4 Manifolds, something like that. So it will be in Dubrovnik in June. So June